All right, let's see. All right, guys, it is not compulsory. Okay, not compulsory to be here. I hope you're here of your own free will. Yes? You know how it is with free will, exactly. It's as long as you sign a waiver that you're doing something of your free will, that's all we need. So here we go, guys. So I think you did receive my message, correct? You did receive my nice morning email. And again, I cannot warn you enough, guys, so that we don't have this misunderstanding, is that last semester people had this misunderstanding with me, which resulted in about 11 people needing to fail the class, and I failed them. Okay, so not a single tweet, not a single letter, not a single share. Maybe I will not discover it's true, you know, guys. I try to keep my eyes closed, or at least have them like a horse, so that I do not think too much about it. But I do at times hear and see certain things. And there were 11 people that decided last semester to try that, and they tried it successfully. That's a small warning. So now back to this topic. So today we talk about one of the most important theorems, guys, and the idea begins here. We know how to calculate antiderivatives for functions like cosine, correct? But how about function like cosine of x squared or e to the minus x squared? How do we accomplish that? Do those functions even have an antiderivative? Those are the questions that we can address using the Fundamental Theorem of Calculus. Now, to attack this theorem, guys, we introduce what I call a cake function, slice of cake function. So the idea here is as follows. So suppose, guys, that I begin with this crust function f of x. This is the crust function, and its picture is, if I change the variable to t, the picture is like this. So this is the graph of y equal to ft. The reason I switch to t and not keep x, I will tell by the end of today's lecture. Okay, so switching variables, changing t or x to t doesn't really do much. It's just a relabeling. Okay, so this is I call this the crust function. And then naturally this, guys, this function I call the cake function. And what happens is that at the position x, you cut the cake, and at the position A, you cut the cake. Okay?
Sorry, Professor. I'm not sure if it's getting cut off for me or it's for everyone else.
Yeah, let's verify that, guys. Can you process what I'm saying, or is it getting cut off for you as well? It's good, yes? I think it's your connection then.
Okay, so I'm going to leave and come back in, see if it's better.
Yeah, try.
Thank you.
And the cake function is just giving us this region of cake. You're asking how much cake you want to get, and this gives you, this cake function gives you, in our case, it's calc1, so you're getting a very flat cake. And this integration is just giving you the amount of cake that you're going to eat, how much cake. Okay, guys? So let's understand a very easy comprehension check. Let's try to do that, guys. For this function, for f of x, equal to integral from a to x f of t dt. For this function, I hope you understood what it does, guys. You see, why do I call it this little f do I call the crust? Because that's the shape of the cake. That's the top shape of the cake. I call it the crust. And this function is just calculating the calories, more or less. If it's uniform cake, it's very proportional to calories. So you say to your lively aunt, right? You say, dear aunt, could I please get x equal a amount of cake? Now, I would like you to, in human language, explain to me, please, what have you asked your aunt to do? You understand? I said, dear aunt, please give me x equal a cake. Where, again, guys, there's one slice at a and another slice is at a. So what have you asked your aunt to do? Here is the formula, guys. What have I asked of my aunt? If I say, please give me x equal a. Exactly. Please, aunt, I'm not hungry. I don't want to eat anything. Because, guys, because look what happens. What's the situation if x is equal to a? F of a, because this is the bottom. It's the integral from a to a, ft dt, which is what? It's in terms of the summation, its limit as n goes to infinity, sum k equal 1 to n, f of a plus k times a minus a divided by n times a minus a divided by n. Are you with me, guys? Do you understand this formula? Again, what's the integration sign doing? You are adding up very short, very thin rectangular slices. They're hair thin. That's why dx is there. And the altitude at position x is f of x. Yes? The altitude at position t is then f of t. So this is what this means. Now, do you see that this limit is just gathering what? You're just gathering, because a minus a is 0, you're just having f of a multiplied by 0. You're adding f of a multiplied by 0 multiple times. You agree? So that must be 0. Now the next question, guys, what happens if you ask, you say, aunt, could I please get x equal to b, where b is less than a? What are you asking from your aunt in human language? Come on, guys, think about it. B is less than A. So, auntie, could you please give me B less than A? Please cut the cake at B less than A. What are you asking your aunt for this function? Here is the definition. Yes, guys, the definition from A to X. Now I am asking for B to be less than A. What am I asking my aunt to do? I want to see more answers. destroy the cake. Okay, let's see what else. Guys, you see, it's very important to interpret. Here is what you're asking. It's something to be concerned. You're asking your aunt to take 2 fingers, place those 2 fingers on your tongue and make you vomit the cake out. So that you're bulimic, you have trouble. You should go to the doctor if that's what you're asking your aunt to do for you. Why is that the situation? Because, guys, look what happens. The integral, now b is less than a. The integral from a to b of f of x dx is what? Do you remember? It's the limit as n goes to infinity of the summation. K equal 1 to n. Now what do? You take the, you begin not a to b, I'm sorry, a to b. So it would be a plus k b minus a divided by n times b minus a divided by n. Are you agree? Are you in agreement with me, guys? Do you understand what I'm writing, guys? The summation thing should be very obvious. I'm just describing how to cut the interval from a to b into many parts and erect the altitudes there, right? This is the altitude and this is the width. Now look at it, guys. B is less than a, which means that I can write this as limit as n goes to infinity, and I will try to make b minus a, guys, is a negative number. Do you see? Because b is smaller than a, b minus a is a negative number. So we have k equal 1 to n f a minus k a minus b divided by n, and this here I can write a minus b divided by n, and I can put the minus in front. Are you with me, guys? I'm gonna do one problem where I solve it just to be sure that with concrete problems, so you can see what happens. Yes? So do you, guys, if you understand, tell me how to interpret this limit. This limit means what in terms of integral summation? In terms of integral symbol. This limit is what? Again, guys, if you do not see it, if b is less than a, this is the way the interval is broken. So this is b, this is a, and this is what we should be seeing. So what is this describing, please? Very good. So this describes, guys, this look at it. This means that I'm starting at this point at A and I'm walking towards B. I'm walking backwards. So this is describing minus the integral from where? The integral from B to A, because I'm walking backwards. Do you follow? Please write Y, because I don't want to make you write 3 letters. Write Y if you follow, or N if you do not. Very good. Very good. You see what happened? We were able to create this integral. Beautiful. So let's do a concrete example just to verify that you understand what's that is saying. So suppose I want to calculate the integral from 2 to 0 of x cubed dx, or let's make it t cubed. Just let's call it t cubed. Okay, now what will I get? So if I apply the definition, it's limit as n goes to infinity, summation k equal 1 to n. Then what do I place here? I have 2 plus k 0 minus 2 divided by n. You see what I do? I begin with this point plus k times this minus that over n, this minus that over n. And what do I get? I get limit as n goes to infinity. This is cubed. K1 to n. What do I have when I cube it? It would be 2 cubed. Yeah, it's 2 cubed plus 3 times 2 times 2 squared minus 2 over n times k plus 3 times 2 times minus 2 over n without the square, and finally plus minus 2 over n times k cubed, and the entire thing multiplied by, which I can factor outside, it's minus 2 over n. Yeah? So what do we have here? We have here then, if you look at the summation, it's minus 2 divided by n times 2 cubed times n, if I sum it here. Then the next one is minus, here we have 2 over n. It should be squared, by the way. So minus 2 cubed n so minus minus 3 times 2 squared times, I can say plus minus 2 over n times k squared is what I need to sum. And so it's 3 times 2 squared. The summation of k is n plus 1 divided by 2 times minus 2 over n squared plus 3 times 2 times summation of the k would be n plus 1 times 2n plus 1 divided by 6 times minus 2 over n cubed, and finally plus, this is k cubed, so summing up k cubed would be n plus 1 divided by 2 squared multiplied by minus 2 over n to the power of 4. So what are we gonna get when we push the limit? By the way, I hope you understand that, I mean, I'm not sure, I selected a slightly bigger number. I mean, there is no way on earth that I would be doing this calculation this way. You see, guys, if you carry a calculation, you're pushed by a particular rule. That's not usually good. You know, you can just always rewrite it and make the expression much simpler. So what is that limit? That limit is, let's see, so the limit is minus 2 to the power of 4. It's minus 2 to the power of 4 plus 3 times 2 times minus 2 squared plus 3 times 2 times 2 times minus 2 cubed divided by 6. And next part is plus minus 2 to the power of 4 divided by 4, or by 2 squared. So when you simplify this garbage, you will see that what you get is minus 2 to the power of 4 divided by 4. Sheesh is, well, I mean, I don't know. It's partially my fault to carry out with this pathway. I'm not sure, guys. You see, I am trying to, here is the thing. A lot of you like concrete numbers. I don't understand why. I don't understand how that helps, right? And it's very the opposite for me. You see, I like abstraction. Abstractions are very easy to manipulate. So for example, going it this way, it's very long. You see, if you realize that what you're doing is you're adding up rectangles, going from 0 makes it much simpler. You see, basically this summation, guys, for instance, this limit that we rolled before. So when I was doing it, I was grinding my teeth because that's a very stupid way of doing it. So this limit, yeah, is the same as this limit. Which is much better. You don't need to go through the process. And what is that limit? This limit is simply minus 2 over n to the power of 4 times the summation k equal 1 to n of k cubed. And that would be minus 2 over n to the power of 4 n plus 1 divided by 2 squared. And then you push it, so then the limit is what? So the limit is minus 2 to the power of 4 divided by 2 squared, which is minus 2 to the 4 over 4. You see? It's just, if you have to understand this very important thing, guys. So you see, before I kind of didn't want to do that. I just carried the calculation. As I carried, I think, how many of you are even understanding what I'm doing? The expansion and whatnot. You have to see this point, guys. If you understand what somebody is trying to accomplish, you can actually do it. You're not forced to walk on a particular path. You can go around it. You can figure out another strategy. But if you don't understand, you're forced to walk and march along a particular road. And that road might lead you into the swamp. Good? It probably already has led us into that swamp. All right, so that's what we understand about this function. It's very easy to calculate this function at A, and it's not particularly easy to calculate this function anywhere else. You might object, guys. You might say, but wait a minute. Can't I just calculate the same thing a different way? So for instance, if I say integral from 2 to 0 of t cubed dt, couldn't I just say, I know the antiderivative of t, and I can write t to the 4, and I write 1 over 4, and I write 2 and 0, and the result is, plug in 0 at 0, so the result is minus 1/4 2 to the 4. Why did I go through the fuss of carrying out Riemann sum? Why did I do that? Would anybody care to comment? Like, couldn't I just do this? Shortcut. Right, I just here, why did I take this limit? Why couldn't I just take antiderivative of t cubed and multiply and just plug in 0, plug in 2, like I told you before? For the very simple reason, guys, that I gave you the shortcut, but you don't know why the shortcut works. It works because of the fundamental theorem of calculus, right? So when you go, when you try to understand how this is developed, you first understand that the integral means taking this Riemann sum and taking the limit. And somehow, magically, it can be also done by that shortcut, which can only be understood if you see how what the mathematics is doing. You see? All right, Cillian, take care. So, guys, this is just an interesting observation. Okay, guys. So I hope are you still with me, guys? Are you not entirely confused? If you have a logical core, I mean, you should understand what I'm talking about, right? We gave the shortcut, but we have given it without justification. I taught it out of order. If you are novice students, the shortcut should be like a miracle. It's like you are so now used to that miracle that you take the miracle for an ordinary procedure. Good? And then here we can observe the miracle in action. Look at it, guys. If I define this function, f of x equal to x, this is my cross function. This cross function has to be changed into t. So that's now the integral from 0 to x of t dt. What is this function, guys? What is this function, capital Fx? Well, if I carry out the Riemann sum process, look what I observe. I observe it is 1/2 x squared. I observe that this function that is written with an integral is much simpler. It's a particular antiderivative of x. The cake function is an antiderivative of the crust. Now, is it a coincidence? Well, I can repeat this calculation with x squared. If I repeat this calculation with an x squared, everything is the same, no problem. Again, I'm not gonna torture you through the algebra. You can do that yourself. Here is the algebra, guys. I end up with 1/3 x cubed. Yes? Which is, again, another particular antiderivative. And with every other example that I try here, that I'm able to carry through Riemann sum, I find surprisingly, or not surprisingly, that the result is a particular antiderivative of the crust function. What is going on? Before we talk about what's going on, guys, I need to introduce one more tool. One more tool, and that has to do with construction. At least I imagine it relates to construction. Suppose, guys, you had this very strange problem. Suppose you were a land surveyor and you had to figure out the distance between the soft ground to the bedrock. And the bedrock in our case is the x-axis. Here it is, you see? That's our bedrock. the surface here is, or the curve here is continuous. So what can you do? How would you find the average distance to the bedrock? So I suggest you walk from A to B, and at regular short intervals, you drill to the ground until you hit bedrock. So the representatives here that you drill at point X is f of X. So different X, it's going to be a different f of X. So how do you carry that average procedure? You see, you want to know what's the average distance from the topsoil to the bedrock, to the x-axis. So let's try to approximate the average by taking n sample points. So what you do is you subdivide this interval into n segments, and at the end of each segment, you take a drill. So x1 is the first excavation site. It's a plus 1 times b minus a over n. X2 is a plus 2, b minus a over n, and so on and so forth. Yes? So what do you do, guys? You take those sample points, plug them into the function, and add the functions up, add those numbers up, and divide by n. So far clear? So far you understand? Yes, guys? How do I average? I add things together and divide by total number in my sample. Yes? I hope I'm not, you're with me. Yes, guys, you understand the distance from the bedrock, from the x-axis to the topsoil is f of x. So I add up averaging f of x1 plus f of x2 plus f of x3 and onwards. Are you with me? This is the formula I get, guys. Now I can write the average formula is then I take the limit. If it's a continuous function and I make those if I make the segments very thin, and I then have a lot of samples very near together, then I will have a very good representation of the actual average. So then I take the limit as n goes to infinity. Do you see that, guys? Again, you do that all the time, not just for this class. If you know how to use calculus, when you truly understand it, you use it to derive formulas that you yourself never saw, and maybe nobody else did. You understand? If you understand this too, you're able to build things that were never given to you before. No, you didn't learn them in a textbook. That's what we're trying to accomplish eventually. So limit as n goes to infinity, this is the average. Do you agree? This represents a good representation of the, this is a good representation of the average of this continuous curve, correct? Now, would you help me please, guys, look at this formula and tell me, what does it look like? This limit formula looks like what to you? Yes, one person right away reacts, guys. And what about the rest of you? What does it look to you like? Okay, let's test it this way, guys. It looks like a Riemann sum, right? It looks like an integral. Do you agree? It looks like we can convert it to an integral. But what's missing, guys? Look at this formula, and there is something missing about it. To be a perfect integral, there is just something that's not there. What's not there? Very good, Alessandro and Erin. And the rest of you guys, do you see we are missing a b minus a? Yes, I want a b minus a here. I know we did not talk about integration for any good duration of time, but I hope you have a sense, guys. It's b minus a that's missing here, and here I write 1 over b minus a, which means that this average, f average, is just 1 over the length of the interval, integral from a to b fx dx. That means if I take the integral of a curve and multiply by 1 over the length of the curve, I will get the average of that curve over that interval. Do you understand? We just derived the formula, guys, that if you understood each step of it, you now know that this integral represents average. That's very, very powerful idea that we're going to use in a moment. I can explain it in other ways or not, right? So Here it is, guys. Now let's try to see, guys, if you can without doing any calculation. That's what by just understanding what something should be without any calculations. Could you please tell me what's the answer to problem A? Okay, guys, think about what it means. Look at this integral. Do you see that we take limit as h goes to 0? So first of all, let's see 1 over h times the integral from 0 to h. Do you see that that the length of the interval is h minus 0, and we multiply by the reciprocal? Yes? So this represents average. And I take limit as h goes to 0. Now what's the average if h is very short? If h is very short, all the x's are close to 0. Do you agree? Each x between 0 and h is very close to 0, which means that that because the function x squared plus 2 is continuous, x squared plus 2 looks very much like the value of this function at 0. Do you agree? It looks very much like 0 squared plus 2. Are you with me, guys? So just the altitude, each f of x, by continuity, it's very similar to the one at 0. Yeah, so this one, look at it. You see, guys, x squared plus 2. We limit as h goes to 0. It means that x squared plus 2, all the x's are very similar to 0. So x squared is very similar to 0 for all values from 0 to h. So we are averaging, in essence, 0 squared plus 2. We are averaging lots of 2's. Now the average of many 2's will be 2. Yes? And if you know the Russian grading system, you understand what that means as well for this class. Good. The average of many 2's, guys, will not be 7 or 5 or, right? So do you understand? So this limit is just 2. Please write y if you understood. How I figured it out, guys, I didn't do a single calculation. You see what I did? I looked at this thing and I said, okay, it tries to make me calculate something, but what is it trying to make me calculate? Whatever I already have here, I have this information. So I'm not gonna bother with the calculation. I'm just gonna figure another way to get there. Do you understand? That's you do very frequently in mathematics. If you're very, very clever, you can do that extraordinarily well. The idea is it's the art of figuring out excuses or other ways to bypass a calculation or bypass a procedure and get to the solution using an entirely different route, and not by cheating. Even though somebody who cheats very cleverly, I do respect it. It's true. But most people do not cheat cleverly. Just okay. Most people are just My God, they just somebody created the machines, and the machines are just doing the work. Like my friend, he has gotten himself a Japanese toilet. Right, this toilet opens its mouth when you come in. It's pretty scary, and I think this thing can probably do better calculus than most of us. All right, so let's calculate this one, guys. B. What is, look at it, the function is split. It's sine x over x. If x is not 0, it's 1. If x is 0, can you tell me, please, what is this limit? What's the limit as h goes to 0 of 1 over h, integral from 0 to h f of x? Please try to reason it out. Tell me what's the answer. Yes, the answer is, guys, what about the rest of you? Yes, Jeffrey. Yes, Jamel. Yes, Moshe. Correct. Correct. The answer is 1. Do you see why the answer is 1, guys? Because what are we averaging? If h is very close to 0, then x is not very far from 0. And sine of x over x will then be 1. So we are essentially taking an average of many, many, many 1s. And that must be 1. You see, guys, so without doing any of the calculations, I just reasoned it out what it must be. So this limit is 1. Could you help me with the limit number C, guys? What is the answer now for C? And notice, be careful, guys. Look at the interval from minus h to h, 1 over h. So let me know what's the answer for C. For C. Come on, you can do it, guys. What is this thing, guys? Well, look at it. Is something missing here? Okay, thank you, Sophia. Is something missing here? Well, look at it, guys. The interval is from h to minus h. So its length is h minus minus h, it's 2h. So what's missing here is 2. You agree? But since I don't have a 2, I multiply by 2. So now what do I have? Whatever is in the parentheses is average. Now, what happens? Do you see? It was not average before, but modifying it slightly, guys, you'll make it an average. What do you see here? You can obviously observe that, well, tangent of 5x over x is approximately what, guys? If x is very close to 0, tangent of 5x over x is very close to what number, please? Everybody should write. Yes. Five. The answer is this is 5. But there is 5 times 2, so this is 5 multiplied by 2, which is 10. You see where I got the 10, guys? Here it is again, guys. You see, I need the 2. And now the average of this function, because I know something about tangent of 5x over x. I know if h is close to 0, tangent is not going to do much to the input. So if x is close to 0, 5x is close to 0. So tangent of 5x is essentially 5x. Yes? Tangent of 5x, if x is very close to 0, is essentially 5x. So this limit is like 5x, over x, which is essentially like 5. But we had a 2 multiplying it, yes? So the answer is 10. Let's see if we improve a little better, guys. The next one may be the hardest, and maybe not. Tell me for D, what's the average for D? Or sorry, what's the limit for D? I didn't say it's an average. You can do it. Come on, guys. Okay, I have 4 people, and all of you are correct, all the 4 people. I hope the rest of you guys understand what's happening here. Look at it, guys. Now, this is, for the last question, it's missing what? It's missing a 3 to be an average. So first I introduced the 3, because it should be 3h minus 0, it should be 1 over 3h, and I multiply by 3 to make this average. Now, once that part is average, I now ask myself, what's happening with this function? Now, if h is close to 0, 3h is close to 0. And if x is between 0 and 3h, x is very close to 0, which means that e to the sine of 6x over 3x is very close to e to the squared. You see, sine of 6x over 3x is very close to 2. So we are close to e squared. So the answer is 3e squared. Now observe, guys, that something else happened here. Notice that e squared is very not similar to 0. Do you see that 0 did not matter much? Because we had like millions or billions of e squares like numbers, and only one number that's 0. So 0 is an outlier. And average is not very good at picking outliers. It completely ignores them. You see, outlier is something very exceptionally rare. Yes? So those examples might happen, but averaging will not pick it up. We are good? I know it's evening, guys. I don't know how it's for you. Now back to the joys of the fundamental theorem of calculus. All right, guys. So our goal is to show that the cake function is an antiderivative of the crust function. You follow? That's what we're going to try to do that. And we can apply the definition of derivative. When we don't know something, apply the definition. So what's the derivative of the cake function? This is the formula for the derivative, and it can be written this way. Do you agree? So far, we are doing exactly the same standard procedure. Now what happens here? This is 1 over h integral from a to x plus h minus integral from a to x. Do you see that this number can be reduced to the integral from x to x plus h of f of t? Guys, are you with me? So everybody understands how I got this step. And this step is just nothing else but the average of the function f from x to x plus h. Now the function is continuous, guys. Do you see the function is continuous, meaning that if h is very small, the average is going to be very much like the value of the function at x. So the result is going to be little f of x. Do you see that? In other words, it's an antiderivative of the original function, provided the original function is continuous, provided the crust function is continuous. Because we are using that idea that average is equal to the value, to the point that we are centered at. And we're centering at the point x. That means that x or f of x is very similar to the local population. You understand? That x is not an outlier. Here is another way to understand. I mean, it's all the same, but another way to understand why that was working, guys. That clever trick is to observe that if if I take the cake function, I remove f of x plus h. From f of x plus h, I remove f of x. And I get this expression. Now, what is this expression? That's the area under the curve from x to x plus h multiplied by the width of the interval. So this shape is very similar to a thin rectangle, guys. So what happens if I take that derivative? It's like I am asking for the area of a thin rectangle, and I divide that by the width of that thin rectangle. Now, if you take area of a rectangle and divide by the width, what are you left with? You're left with the height. You're just left with the function f of x. Do you understand? So it's like, look at it. This integral is very similar to the function, to the rectangle, whose altitude is f of x and whose width is h. So 1 over h times f of x h, that's the area of that rectangle, is approximately f of x. That's the idea of that theorem. How is that supposed to work? So here is how the shortcut is developed from here, guys. And that is, let me know for sure if there is something you are not understanding. Suppose I want to calculate the integral from 0 to 3 of x squared dx. I'm going to explain why the shortcut works now. Okay, so I mean, obviously you can say, well, write x cubed and plug in 3 and then subtract, plug in 0. Right, but I'm explaining why that's supposed to work. So first of all, look at this function, guys. You see, instead of looking at this value, I can create the function integral from 0 to x t squared dt. And then the integral from 0 to 3x squared dx becomes 0 to 3 t squared dt. It becomes just evaluating the capital F function at the point 3. by the fundamental theorem of calculus, the derivative of that function will be x squared. The derivative amounts to just taking this x and putting instead of t. The derivative of this function will be x squared. You understand? In other words, this in this area function, this cake function is just a particular antiderivative of x squared. And I know certain antiderivatives of x squared. I know that 1/3 x cubed is an antiderivative. Yes? 1/3 x cubed. Here it is. It's an antiderivative. Now, do you see that all other antiderivatives must be 1/3 x cubed plus a constant? Do you see that, guys? Because derivative completely encodes the shape of the curve. Do you see that? So if two functions have the same derivatives, it means that we can consider a curve as if it's built of a line segment, right? For instance, let's try to draw that picture, guys, and I'm going to ask you if those two curves have the same derivatives. So here is one curve, and here is another curve. Do those curves have the same derivative? Why or why not? So first, do they have the same derivative? So this is curve 1, and this is curve 2. Do they have the same derivative? This might be given by y equals to ax, and this is y equal bx. Let me maybe even draw you a better drawing here, maybe so that the answer is more obvious to you. Do those curves have the same derivative everywhere? Maybe somewhere they do, but my question is, do they have the same derivative everywhere? In other words, can I conclude that a prime x equal to b prime x? I didn't give you a formula, guys. So how do you know you can conclude the answer is no? You're so certain. What makes you certain that the answer is no? I would like you to explain to me, if you could. Yes, that's kind of good. So look at it, guys. What I imagine personally is that this curve is made of line segments. I purposefully draw them large so that you can see them. And this is made of line segments, yes? Now, this is the line segment I want to focus on. Here it is. Let's focus on this line segment, you see? So for this x, we have this line segment for B, and we have this line segment for A, for the curve A. You agree? And those line segments are not oriented the same way. Do you agree? One is steeper than another, so their slopes will not be the same, and therefore derivative, which represents slope, will not be the same. Do you agree? Now, what must be the case if I drew two curves that are whose derivative is the same, guys? If I were to draw another picture with two curves whose derivative is the same, what must be true about those two curves? They will be parallel. Do you see, guys? Because of this, anywhere you look, you find the line segment for one graph, and you must find the line segment oriented the same way, the same slope. Then it could be the same exact function. It could be lower or higher. What does it mean? It means, this is what we're understanding geometrically, it means that all antiderivatives must be the same, except for a plus constant. They can be, the shape must be of the graph is the same. So it's either higher or lower. You understand? The same repetitive sequence of line segments. They just begin from a different point, possibly. Are you following, guys? I try to, without mean value theorem or other ideas, geometrically to explain to you why, if the derivative is the same, that means that the functions must be the same. The curves must be the same, therefore the functions must be the same. I hope you understand. Very good. So you see what I do, guys. So how do I use that idea? It's enormously useful for my advantage. I just hope you realize just how genius the result is, how much I am avoiding. So you see, I am trying to avoid doing Riemann sums, which you noticed is tedious and hard, right? So directly the integral from 0 to 3 of x squared dx, I just have to add up the areas of rectangles. But instead, I try to find a different pathway. So I say capital F of x is the integral from 0 to x t squared dt, and I see that what I want to find is this capital F evaluated at 3. And then I use the fundamental theorem of calculus to conclude that capital F prime is just x squared. The derivative of this function is x squared, do you understand? And what does it mean? It means that, that this function must be 1/3 x cubed plus c. I figured out a very simple formula for that function, not involving integrals. You see what I did? And I did it because if the derivative is x squared, then it must look like any other antiderivative of x squared. It has this, if I drew the graph for this function, it would look like some antiderivative of x squared. Now, what specific antiderivative I need to, for that I need to find c. You see, so it's 1/3 x cubed plus c, but which specific c? Because I need to calculate f of 3, I need to know c as well. So what am I gonna do, guys? For this situation, it's nice to plug in 0, do you see? Because integral from 0 to 0 is 0. I know that this function at 0 will equal to 0. And if I plug 0 here, it would be 1/3 0 cubed plus c, which is c. So c is 0. So this function is actually exactly 1/3 x cubed. And what's the value, and what's this integral? This integral is just f of 3, which is 1/3 3 cubed, which is 9. So without doing Riemann sums, I figured a way to go around it. I verified what is the antiderivative. Yes? That is what happens in general, guys. So let's see the general situation, and then I'll give you one more concrete example to see how we avoid doing integration, okay? I hope it will be easier, or it's something that you'll be able to follow. So here is the general situation, guys. Suppose I want to integrate from a to b little f dx. So instead of doing that process, I actually modify and I create a function, capital F. And I call it capital F A. And that's the integral from a to x f of t dt. Now I know this is an antiderivative of little f, and if I'm lucky enough and I am able to find another antiderivative, call it capital F, then what do I see? I see that capital F sub a is capital F plus c. And how do I find the constant c, guys? What value do I put in? Obviously, for this function, only the little a is the easy value. So I put little a, and that makes it 0. Do you see that? And putting little a in this derivative, I have capital Fa plus c. So that means that c equals to minus capital Fa, which means the function equals to capital Fx minus capital Fa. It's equal to the other antiderivative at x minus that antiderivative at a. And that means the integral from a to b is equal to what? To capital F sub a of b, which is this formula, which is that shortcut. You see, that's the shortcut we learned. Now let me show you with a concrete example what this is saying, guys, and how useful it is. Imagine you come to calculus and I did not teach you that shortcut and nobody did. And this was the question. You had to integrate from pi over 3 to pi over 2, the function cosine x dx, okay? So if you don't have this, you go by definition, you go, oh, let me try limit as n goes to infinity, summation k equal 1 to n, and here I have cosine of pi over 3 plus k pi over 2 minus pi over 3 divided by n times pi over 2 minus pi over 3, that's the length of the interval, divided by n. Yes? That's what I will do if I try to accomplish it by definition. And what's going to happen, guys, it's intractable. You're dealing with a very difficult limit and you have no idea how to go about doing it. Right? If this were assigned to you and you did not know a shortcut, you will be stuck. You would have been stuck. Do you agree? That's a dead end because I'm not able to go much from the definition. It's very difficult. Now, what's the idea from the fundamental theorem of calculus? How genius that idea is, you see? Well, I say, okay, so step one, I'm defining this function. I'm defining capital Fx to be the integral from pi over 3 to pi over 2 cosine, to pi over, so to just simply x. Cosine t dt. Good? That's what I define. Now, that's my first step, guys. Now, I observe, secondly, that by fundamental theorem of calculus, which I hope you understood why it worked, guys. If you need to establish it on your own, then you'll know why it works. The derivative of this function is equal to cosine x. I will later explain why I switch to t. Why don't I keep x, but I switch to t? That's technical. I'll explain at the end. Okay? But I switch to t. So the derivative is cosine x, which implies, guys, that the function has a very simple formula. The function has the formula sine x plus some constant, which I have to determine. You see what I did, guys? I entirely go around figuring it out. I'm saying, well, I know this is an instance of evaluating the function. I will need to later evaluate f of pi over 2. That's what I'll need to do. But first, I'm trying to come up with a very simple way to use this function to avoid Riemann sums. So I see this function is capital F of x equal to sine x plus c. Tell me, how do I obtain the c, guys? What value do you plug instead of x to figure out what must be c? Guys, what do you plug in to get c? Look at the original function. There is only one value at which it's very easy to evaluate. Look at this capital F. Well, look at it. Look, y0. Look at it. What do you plug in here to make it easy to evaluate? This function, guys, it's only easy to calculate at one number of x. The bottom number is pi over 3, and then this is x. What x is it easy to evaluate? Guys, what's the best thing to do if I offer you poison? Answer that as well. Or if you cannot answer this, answer what's the best thing to do if I offer you poison? Not take it. Don't eat anything. So if this nice auntie, or Snow White, she's offering Snow White this cake, take from my cake. What do? You say very politely and mathematically, you say, what do you say? Because mathematically, your aunt is a bit challenged. She doesn't understand. At least my aunt was. She would not understand if you say, I don't want the cake. You have to say, oh, please give me x equal to. In other words, slice the cake. One slice is at pi over 3, and give me another slice at what value? Yes, pi over 3. Slice twice at pi over 3, and then I get 0 cake. Yes? So the answer is that I will see that 0 is equal to f of pi over 3, which is sine of pi over 3 plus c, which means c is equal to minus sine pi over 3. Do you see what I just figured out, guys? I now know the function. My cake function has a very nice formula. It's sine x plus c, which is then sine x minus sine of pi over 3. Do you see what I just figured out? And then I want to calculate what's the function at pi over 2. So that means just simply sine of pi over 2 minus sine of pi over 3, which is the same, guys, as you know, as sine x evaluated from pi over 3 to pi over 2, because that's that procedure, that shortcut procedure, is the fundamental theorem of calculus, doing its job. Does it make sense why that rule is working? Look at it. Instead of doing Riemann sums, instead of calculating this complicated summation and finding closed forms, what do? I skip it entirely. I say, okay, this function, whatever this function is it's an antiderivative for what I'm trying to integrate. So let me find a simple formula for the antiderivative and use that. That's the shortcut. And I hope you understand, or try to understand, the shortcut, guys. I don't know if maybe maybe I'm being optimistic here. Semester is almost over and it will never be opened, a calculus book, I mean. But it's too bad. All right, Claire, nice that you came. Thank you for, maybe you already left. And here, guys, this was something that I had a student. It was, I think, back in 2014, a long time ago. I had a student and I asked my questions for calculus about maybe more or less this way. I said something like solve. Yes, and the student did not do like I intended. He solved those questions, all of them. He solved not like what I intended, and I gave that student 100. And he basically did 0 work on my exam. What did he do? I gave him those points because he was clever. He understood something that other students, I guess, did not understand. So guys, what do you do for question A? So let's, come on guys, I hope you're not dying there. You're not so confused that you forget even what you know or what you imagine you do. If you had this question, what would you say for cosine and whatnot? All right, very nice. Safa, why are you afraid, guys? Nothing to be scared of. So a lot of students write sine x plus c, and that was my intention that they do so. Yes? What did that student do, guys? He looked at this question and he said something, 0 to x cosine t dt plus c. And I gave the person, of course, I mean, the question is find an antiderivative or find all antiderivatives, and he did. He just did not express them in a nice way that is more usable. But he definitely answered the question. He realized that 0 to x cosine t dt is an antiderivative for the function. Do you understand, guys? The point is, if I say the answer is sine, I actually am able to use that formula. If I am saying this, I'm not necessarily making good use of it. I'm not necessarily more capable of doing something with it. Yes? So then we answered all those questions the same way, and some of them, guys, cannot be answered in a better way. So for example, this, try as you might, you will not come up with a simple formula. But if you write something like 0 to x e to the minus t squared dt plus a constant, you have in fact immaculately, what's it, without there being any reason to find blame with you, yeah, you have indeed found an antiderivative, and you found all of them. If you find one antiderivative, all the others you are also found. Yes. So a lot of those equations, I mean, can be solved this way. You see, I can just do this. Now, guys, last stretch. Can you tell me what's the derivative for A? Very quickly, what's the derivative for problem A? I think on your exam, you might see such question somewhere. All right, guys, do you recognize what it is? It is, you need to find the derivative of this function. Yes, so it looks like integral, it looks like the cake function for secant of t dt, into which you plug in, instead of x, you plug in x to the 4. Yes, so how do you solve this? It's just chain rule. Look at it. Here is the function, guys. Here is the cake function, and into the cake function, I plugged x to the 4. So the derivative is of capital F of x to the 4, which is the derivative of the outer function times the derivative of the inner function, which in this case, when I take the derivative of this function, I end up plugging x to the 4 instead of t, and then multiplying by 4x cubed. Do you understand? It just, you take this you take the upper bound, the function, you plug it in, and then multiply by its derivative. Could you please calculate B? I hope you understood, guys. It's here. It's just secant x to the 4 times 4x cubed. Could you now tell me what's the answer to B? Abraham, are you holding? Is your internet, your phone is holding?
it gets disconnected here and there, but it's not as good as my computer.
All right, one answer is available. What about the rest of you guys? Safa, you need to replace t by x. That's the idea. T is not existent. I'll explain in a moment. Okay, I know it's a lot of information very suddenly, but I hope you can read the notes or prepare a little before and that you follow, guys. All right, so what do you get? Yes, very good, Jamal. Jumarl. No, not right now, Abraham. You're on mute. All right, guys. So indeed, the answer to problem B is simply plug in x instead of t. So it's 1 over x cubed plus 1. Now, can you do problem C, guys? Can you figure out what to do for problem C? All right. So let's see, guys, you have to be a bit careful. Do you see that x is on the bottom and I want it to be on the top? How do I make x go on the top? I multiply by -1. So this is what I do, guys. You see, I multiply by -1 and now x is on the top. And now the derivative allows me to put in x instead of t. So it's root of 1 plus secant x. Now can you do d? Very similar. You see, it should be negative because I multiplied by -1 to get the function to the top. Very good, Alessandra. Alexandra. All right, so how do you solve question D, guys? So you move you swap one and sine, so it's minus derivative of sine on the top, and then when you push it in, it's 1 plus sine squared with a minus, and then derivative of sine is cosine. Do you see that? Derivative of sine is cosine, so it's that, let me see if Alessandra, you forgot times cosine. Yes, you forgot, well, there is one mistake. Because it's this function and then chain rule derivative of this function. Now, guys, can you do E? How do you do question E? All right, guys, how do you do E? Think about it. What you remember that property that you can break an integral and make a constant, right? There is cosine to sine, and there would be, if you had a constant in between, you can break the integral. And that's what we are going to do. Look at it. We will take cosine to c plus c to sine, right? You see that? Now, if you remember my previous lecture on Tuesday, c does not have to be between cosine and sine. It can be any number. Doesn't matter where. So we have this. And then this part I'm going to write this first, and this part I will write second, and with the minus. So what happens is then it's sine going in here times derivative of sine, and cosine going in here times derivative of cosine. And in general, guys, the derivative from ax to bx of the function is the function evaluated at bx times b prime minus the function at ax times a prime. So once you learn the procedure and you figure it out, you don't have to break it and waste time on steps. It's just plug this in, and then multiply by its derivative, minus plug this in and multiply by its derivative. See if you can do this number f fast. Good night, Jomaro, sorry, that I'm hard for me to pronounce. Take care, Jomaro. Guys, very simple. What's the derivative of this thing? So here it is. Just take the top function, plug it in. So it's instead of t, you plug x cubed, multiply by the derivative of x cubed, and then minus plug in x, the derivative of x. Here is your function. Yes? And then there is g, the derivative of this. You can think on your own. You can look into my notes. Do you want, or you're not in the mood anymore, do you want to understand why I change parameters? Why I not just keep integral a to x, f of x dx? Why do I change to t? Do you want to listen to that, or you had enough? Let me know. Yeah, okay, so I see. Okay, just quickly, guys. In the mood. All right, guys. If you want to stay afterwards to play a game of what, when, where, or to say goodbye, or or anything else, or some questions, you stay. And if you don't want to listen to this, I wish you farewell. I hope you will do very well on the 25th. I will explain why this works for those that are interested. Okay. So why do we change to t and not stay with x? So here is what happens, guys. Suppose we are going to compare the function where we have the t, and we're going to have the function, let's say 0 to x. We have the same crust, more or less the square crust, and we're going to have two cake functions, g and f. And let's try to understand how those functions are different. You see, so let's calculate f1, f2, f3. What happens? I plug in 1 only as the upper part of the integral, on the upper number of the integral, and 3, right? So here you can see what happens. I mean, I am integrating always underneath the curve. Whereas if I do that for g, look at it. Wherever I have x, I have to also replace it by the number. So g of 1 means integral from 0 to 1 of 1 squared. At 2, it's integral from 0 to 2 of 2 squared. At 3, from 0 to 3 of 3 squared. Are you with me? And what am I end up getting, guys? Look at it. Here is the g function. Instead of integrating under the area for a given x, I end up integrating the value of the function, basically a constant. So it's always a rectangle. Do you see? This is what? A rectangle. It's 2 squared times 2. This is 3 squared times 3. So in general, for f of x, I get 1/3 x cubed, but for g, I get x cubed. I get an entirely different value. Do you see that? So the reason I switch to d is for you or for the machine to not make the mistake that it needs to replace, because it will replace each instance of x by the number. But you don't want to integrate under a different curve. If you replace this by the same number as that, you see what you will get, like 1 squared, 2 squared. At each instance, you are just integrating a constant function. 2 squared is a constant function. 3 squared is a constant function. So the thing that you are actually inevitably communicating is the area of this rectangle. You see, you want this, but you really here convey the area of a rectangle. So for instance, at this point, if I evaluate that 2, it would be this. You understand? Rather than be this. It will happen no matter what you wish or not. It just happens because it's very similar to in English when you use the word eat too much. And you don't even notice that the word eat now refers to an entirely different object. So it's to avoid unintended miscommunications, you switch it to t or to some other letter so that you know that you only replace the bound of integration, but you don't bother the function. Is the explanation clear enough? Yes, you see, so that's only technical, really. That's all it is, nothing more. All right, guys, so do you have any further questions? I will stop the lecture. So the final is naturally cumulative. So it's everything. Have you started reviewing, guys? You have the advantage of slightly more time than the other students. They have the exam tomorrow. You have the exam, and I hope it's correct. I mean that nothing strange will happen. You have the exam on May 25th, I believe, from 6 to 8. This is our last class, yes. Well, when I go to a museum and I see paintings by Kazimir Malevich, I will think of you. You will get the grades, guys. I'm sorry that I take long to grade your exams, but I'm rather backed up in many ways. So, so I will be just grading your exam. And once I'm done, you will receive a message from me with your score. You got 100 for the second exam, that never was. And your challenge is to survive the final. Right, Alexander. Okay, guys, if you, I'm sorry, I always mispronounce your name. It's Alexander, of course, right? But Alexander is the more familiar.
This is just a Belarusian spelling.
Sorry?
It's just a Belarusian spelling, transliteration into Latin alphabet. So Alexander, so it's, yeah.
So how do you say it? How do you say your name?
Alexander.
So Alexander.
Like in Russian, yeah, it's just a Belarusian way of how they transliterated from Belarusian language into Latin.
Okay,
yeah.
Okay.
Yeah.
Okay, much easier. Good. I didn't mispronounce it too many times.
It's just like an official. But...
I see. Good. All right, guys. It was nice seeing you. If you want to, we can play a nice round of what, when, where, or two. And if not, then I wish you all the very best. I hope you do very well in the exam. I hope you don't remember and curse my name, but it's okay. You'll forget about it, even if you do. Take care, guys, if you're not staying. So who wants to stay for what, when, where?